Okay, I think we can start. It's 9:04. So I will start with a brief introduction of our guest or our speaker today. So first of all, welcome everyone to this IVM seminar. Today we have Bingwen Hu from which is a professor who is a professor from East China Normal University in Shanghai, where he is also the deputy director of the Laboratory of Magnetic Resonance. So just briefly about his career. So he studied in China for bachelor's and master's degree in Fudan University, but then he moved to France to get his PhD, and in particular he worked in the ultra high magnetic field, ultra high field nuclear magnetic resonance center in Lille in France. And there he developed new methods for NMR. He then returned to China, where he developed a career there till, as I said, becoming a professor. And his research focused mostly on new technology for NMR and EPR, and especially their application for studying batteries. And this is exactly what he's going to talk about today. So Bingwen, welcome, and the floor is yours.
Okay, thank you for the introduction, and nice to meet you, everyone. And today I will talk about a little bit about how to use EPR, NMR, and EPR imaging for lithium-ion batteries. I come from East China Normal University, and maybe after 2 or 3 minutes, I will turn off the camera to not to use too much. And I will slightly introduce the batteries. People usually know about lithium batteries, also sodium-ion batteries. So here you have this kind of aluminum foil, and on this part you have the positive electrode, and you have this kind of electrolyte between the positive electrode and negative electrode. And here you have the copper foils. Normally, what you want for the batteries that use a large capacity, faster charge capacity, or have a long time, such as you can use it for 10,000 days or 10 years. And for the battery research, normally the people use NMR to study this kind of non-magnetic elements or some kind of alkaline metals. People normally use the NMR to study lithium, sodium phosphate, oxygen, nitrogen, or cobalt. And also you can use EPR to study this kind of transition metals, especially in batteries. Also, you can study these radicals such as cobalt, lithium, or magnesium, etc. And this is the nucleus. In the middle, you can use EPR or some other techniques such as synchrotron to study it. But from this part, you can use the EPR to study this kind of lithium metals, or you can use NMR to study this kind of so-called lithium ions. From the right part, you can use the NMR. Most frequently study the nuclei and carbon and nitrogen, etc. The first part, I will talk about how to detect the trapped oxygen gases, which is interesting for lithium-ion batteries. I will start to introduce the background that what's the oxygen redox. And in the lithium-ion batteries, you can use the metal ion redox, such as cobalt, and you can achieve the capacity roughly around 100 to 4,000 mAh per gram. But if you activate the oxygen redox, that here, that means that here, if you replace some if you replace some metal ions with the sodium, then you will activate the oxygen redox. Then you will get another capacity for an oxygen redox, or then you will achieve 290. But the main problem is you have introduce this kind of oxygen reactions, we introduce much more faster capacity decay. So that people are care about the chemical states of this kind of oxygen species. The first proposals about oxygen species was proposed by the telescope in 2015. He proposed that the two oxygens will come together, and then this becomes a peroxide-like diamond. So we call this one is an oxygen diamond effect. And in another cases, some people also, such as Chu, has developed some techniques. They said if the some metal ions move, and then these two oxygen will come together to become this kind of oxygen diamond. Another proposal is that, and we have lithium oxygen lithium configurations. If these two lithium ions will move from the oxygens, and then they will become a localized oxygen host, and this oxygen host has higher energy than the transition metals, and you will involve in this kind of oxygen redox. So this is oxygen redox here. And the latest one was proposed by Bruce in 2020. He said he observed signals at the high voltage here, and he observed this kind of spike-like signals. And these spike-like signals are much more similar to the signal of the molecular oxygen. It is a kind of signal from the oxygen gas. And so he ascribed this kind of signal to molecular oscillators. So he proposed this model here that you can observe this kind of signal here. And he used this kind of technique for the RIGS, resonant elastic X-ray scattering. The main problem is that does RIGS really detect oxygen gas? And these RIGS will detect other species which are not oxygen gas, but they were considered as oxygen gases. And of course, there are reaction pathways because Bruce proposed this kind of pathway here. Then we'll go back to this system because it's much more famous. And this is the first system started by telescope. It started by the XPS and EPR. And then he observed this kind of signal here, and then he ascribed this kind of signal to oxygen diamond. And of course, in another system, for ethane system, he used STEM techniques, and he observed the shorten of the distance between the two oxygen nuclides, such as this one. So he ascribed this one to be an oxygen diamond. But Bruce also started a similar system, and he slightly changed the intent of the solution. And he also get this kind of spike-like signals here. So he ascribed this signal to be oxygen gases. So in this system, we have two assignments. One is the diamond, another one is the oxygen gas. So the first question is that, can we detect oxygen gases in the cathode materials? And there's a very old paper, 1950, proposed by Lobot, Bingwen and Picasso. He used this kind of EPR to detect oxygen gases. We repeat experiments and we acquire this kind of sharp signals, and can also apply this kind of signal to value in the oxygen gas. So we can repeat these experiments. Another one is that we come back to the system. We started the three systems here. First one is this one. And then we decrease the content of lithium to 0.25. You can see here that there's a platform here, and this is much more like a generation of oxygen gas, but we have to use the EPR to detect. So we use the EPR and at low temperature, we can detect the signal. Only in Lucian 0.25, we can detect the signal for Lucian gas, for the oxygen gases. For the other two contents, we cannot detect any signals for molecular oxygen. Of course, we can use the EPR to detect the oxygen dimer, and such as this one. This is a kind of oxygen dimer signal. If you decrease the content of Lucian, you can get a much more broad system, a much more broad line shape here. So we propose a new mechanism. If we have a lot of Lucians in the system, and at the end, you will get this kind of dioxin dimer, which bind to the Lucian. But because of the Lucian oxygen bond, it's a very strong covalent bond. So it's not easy to detach the oxygen from the Lucian. But if we have a lot of if we have a lot of tin inside, that means that we have a lot of tin inside. But at the end, you will get this signal, which that the oxygen dimer was bind to the tin. But the tin oxygen is an ionic bond. It's much less covalent. So these two bonds will detached, and then you will get this kind of molecular oxygens. So we propose this mechanism why we get this kind of molecular oxygen gases here. Of course, we can combine these two systems here. This is in fact a kind of oxygen dimer with the valence of 2 minus. This is the oxygen dimer with the 1 minus. This is if you generate a lot of molecular oxygen gases inside, and then you will get this kind of charge and discharge curve, which maximum hysteresis. Well, and then we come back to the signal that why we get this kind of leak signals is here, and we ascribe like the leaks should not detect the signal from molecular oxygens, but you will detect this kind of oxygen dimer, which connect to the Lucian. So this is a model that we proposed. And so this is a summary that first, the EPR signal results are not consistent with the Lex results, but we think EPR is much more easy to use to detect this kind of molecular oxygens. And recently, there's a new paper published by Telescott, maybe two days ago, and he showed the different kind of Leak spectrums for different kind of samples, such as this one and NCA samples. Because normally this kind of samples does not have this kind of oxygen redox, so they will not generate oxygen gases. In fact, so he said maybe the molecular oxygens is not the direct product of the electrochemistry, but much more likely to be the result of co-excitation in the leaks. For this reason, it's necessary to consider the possible dissociation of this kind of MO-like substance on the beam excitation, which agrees with our proposal that most of the time leaks maybe have much more stronger beam excitation. Then he breaks this kind of molecular bond from the metal to the oxygen, and then this will generate a lot of oxygen gases inside. So this proves that EPR is a much more powerful tool to detect this kind of molecular oxygens. And then we are talking about how to start another system, because in this system we can have this kind of oxygen gas generated, because this tin oxygen bond is a weak covalent bond. But we have another system here. We don't have anything inside. It's purely only have this kind of Lucians inside. It's all stronger covalent bonds, but we still get this kind of a lot of oxygen signals here. So what's the driving force for this kind of a generation of oxygen gases? So we propose that is due to this kind of strong magnetic frustration. I will not go to the details of the magnetic frustration. This is because this is the small triangle. This is small triangle. We will generate this kind of magnetic frustration, because if you have spins going up and you have another label spin, we are going down. But in the third one, you have been in trouble because you cannot balance. But there are another situation that, and this is for this kind of sample that, and this transistor metal was replaced by lithium ions, but there's still a large triangle which we still have this kind of a magnetic frustration effect. This is why we propose that there's still some magnetism frustration in this kind of system, but we have to use different techniques to prove. So we use a squid and to detect the magnetism effect, and we plot the signals here. And this is the index, magnetic frustration index. You can see here, right? When magnetic frustration index are larger than 10, then we call it there's a strong magnetic frustration. At the beginning, it's 300. It's much more larger than ordinary one, and then we will decrease and then come back. But you can see here from C5 from here, and then you will get a abnormal, because you cannot observe this kind of index, but you can still observe a large decrease of this kind of theta value. This means that the magnetic frustration has been greatly released, and we acquire a signal from the EPR. First, we can observe that the signals here, this may be due to the oxygen dimer, and in here you can see a lot of signals for oxygen gases. So this is the signal for oxygen gas. That means that during this time, if you want to release the magnetic frustration, and then system will generate this oxygen dimer and the oxygen gases, which is consistent with a change of the strong magnetic frustration. And you can also see this kind of change of the G value, this abnormal one, the change of the G value, and a change of kind of this signal here, the intensity here. And we also, you can use the NMR to detect the change during this period. And then during this kind of period, which generate oxygen gases, you can get a lot of disorder, because at the beginning, there's a very, it's narrow peak, but after this kind of generation of oxygen gas, then the system will become the disorder. You can also observe this phenomenon in the XRD, such as here. And so we propose a signal that, and the phase transition will lead to the increase of the magnetic frustration. And then in the state of magnetic frustration, the energy is very, very high. So the system want to stabilize the energy, to low down the energy. So the magnetic frustration will drive the generation of the oxygen dimer and the oxygen gases. This was proposed like this one. And this is the oxygen dimer. If he shared the electrons with this spin, with the spin lithium, and then he will low down the spin. And at the end, if this oxygen dimer was released as oxygen gases, and then the spin of the lithium will further decrease, and this will decrease the magnetic frustration between different kinds of nuclei. And then this will reduce the system energy. And we also observe the decrease of this kind of valued after you cycle the 10 cycles. So this improve at the decrease of energy. It's very consistent. And last, we will introduce how to use for the sodium batteries. And for these systems, we still observe the signal from the oxygen dimer, and we also observe the signal for the oxygen gases. And we observe the existence of these two signals. And if we change the electrolyte, such as you change from this kind of traditional carbonate electrolytes, you will get a lot of oxygen gases. If you change to the highly fluorine electrolytes, you will get less oxygen gases. And if you can also apply the NMR, you can see the loss of the signal of the lithium and loss of the signal from the sodium ions. So we still confirm that we propose this kind of reaction pathways that we can change from the HORA to the dimer and then to the oxygen gases, which is different from the proposal from the rules. And last, we confirm that in the lithium-rich system, we can still get a lot of trapped oxygen gases. And for this kind of O3 system, at very high voltage, you can get a lot of signals here. This is the oxygen gases. And with another system, we call the O2 system. This kind has suggested that because in the O2 structure, there's no reversible the TM outplane migration because the magnetism cannot move to another plane. It just vibrate in this plane. He said that this will quench the generation of the oxygen gases. But if we do the experiments, that we can see that a lot of oxygen gases here. So that means that in plane motion of this kind of metal ions cannot prevent the generation of the oxygen gases. EPR can be also used to detect oxygen vacancy, but we not go to the details. And this is lithium cobalt systems. You can see this kind of oxygen vacancy. And at the beginning, you can see a lot of signals from the surface cobalt signal or this kind of CO3 or 4 signal. This is a proposal. I'm not going to the details. And you can also use EPR to detect things like oxygens, such as in this kind of lithium air batteries and the lithium ion batteries. The oxygen gas will combine with the lithium to generate these two species. And by these two species, will decompose into the single oxygen. And if you use this kind of oxotemp, and he will combine with the single oxygens, then you will get a lot of signal from this kind of tempo. And this is execute the EPR. You can see the generation of a lot of single oxygens if we use the carbon tube. But if you add a lot of cobalt oxide, then we will get a less single oxygen. We can also do this kind of in situ EPR to compare this result. The second part is that I'm talking about the lithium plating, and this is the cathode, this is the anode, and this is the separator. And if the lithium moves from the cathode to the anode, and then sometimes you will generate this kind of lithium plating phenomenon. And the most important thing is that if the lithium plate on the surface of the anode, and sometimes you will growth, and then the growth will lead to this kind of lithium dendrites. And if the lithium dendrites will penetrate the separator, it will cause a fire or explosions. So we will try to avoid this kind of uneven lithium deposition. And we can use the different techniques to study this kind of lithium dendrites if by actual tools. The most famous one is the cryo-TM. And such as E-Trade has used this kind of cryo-TM to study this kind of lithium dendrites here. And sorry. But the most interesting one is to use the in situ techniques, such as in situ MRI, in situ Raman or optical one. Also, you can use in situ EPR imaging. But in most cases, you have to observe the lithium plating by the side view, like this one. You look like this way, because the light or electron cannot penetrate these two foils. So they are aluminum foils or copper foils layer. So it's very much more difficult to observe by the front view. So you have to observe this kind of side view, such as in situ GM. So this is basically the situation that the most techniques are observed like this one. It's the side view because the line electrons cannot penetrate the copper or the aluminum foils. And normally people are remove this kind of separator because you will not allow you to observe. But the main problem is what's the lithium dangers between the main mountain. So people want to do like this one, and this is so-called the tally fit system. So you have this kind of separator here, and you look like this one. You want to observe this kind of lithium dendrites by this kind of sort of top view or front view. And is there in situ methods? Yes. The first one was proposed by Gregory and Drexler, and the paper was published in Nature Materials and used to cope lithium foils, and by the this kind distortion here. These two lithium plates connect to each other because normally for MRI the resolution is in this millimeter level, so it's not easy to achieve very high resolution. And but we can do this kind of modification with the one-dimensional imaging that was proposed by Saladrate, and he called this kind of a chemical shift imaging. So you can observe the chemical shift change along the z-axis. But this is 1D imaging, and you can increase resolution, but you will lose the information on the XY plane. And the first one, EPR imaging, was proposed by the Telestrom and Rosen, and he used this technique to observe this system, which I was told before. He also do this kind of side views, but we know that the X-band imaging has a higher resolution, and because at the beginning, the people always use the 2D coils, and so you have to modify it. So is it possible to observe this kind of lithium deposition with a front view? Yes. So we can use this kind of 3D coils. And we publish a paper from JPCR, use this kind of XY plane imaging and YZ plane imaging. So you can do this kind of two imaging in the same time. And then we can observe this kind of lithium depositions on the copper foil. And in the first chart, you can see that at the beginning it was placed on the top, but the most after several hours, you can see a lot of red spots here. This is much more dangerous because they are in high, they are very high. If you discharge it, and then you will get this kind of dead lithium here. So basically the front view imaging has a resolution much more higher than the traditional 3-dimensional MRI. Of course, you can observe in a second chart, you can see that the second lithium also plays on this region. And if you discharge it, you still get a lot of that regions here, and you get a lot of aggregations. And if you take the photo, if you disassemble the battery, you can get a photo. This is empty, and EPR is also empty. But then here you can see the very strong spot here. Why we cannot observe by side view? Because if you by side view, you get this signal here, but here is very, very strong, but the most dangerous one is here. So it's much more important to use 2D imaging. And the second one that we can use for sodium dendrites, because we try to also use for sodium dendrite if it's possible. And we use this kind of technique here. And if the sodium was placed on a copper foil, then this battery is not stable. But if we coat the copper foil with this kind of KJB, in fact, it's carbon materials, then this battery works much more stable. Of course, we can use this kind of coated samples with another cathode MEP, and it also works very well. And we want to observe why he works like this one. And if the sodium was plated on the copper foil, then you aggregate into the center, becomes much more stronger in the center. So we call this kind of central accumulate aggregation behavior. But very interesting, we observe different things on the KJB coated copper foil. At the beginning, it's very strong, but after several cycles, you can see the signal has been self-leveling. So we call this kind of behavior as progressive self-leveling behavior. And we can also use NMR to detect different kinds of sodium metals, such as if you coupled on the sodium copper foil, you will get a lot of dead sodium. And if you have a lot of, but if you coat it with KJB, you have more SEI, but less dead sodium. Well, I will not go to the details. Last, we are going to talk about how to detect the dangers on the surface of the graphite. And this is, first we had do some EPR imaging for graphite. If you charge very slowly, this is like 5 hours. And then the center will be in very red color, strong red color. But if you charge very fast, this is in 15 minutes, and then you will get a light light. This means that very low SOC degree. This means that a lot of lithium ions are not inserted into the graphite. So this will cause a lithium plating behavior. So we use the EPR, in-situ EPR to observe the in which rate we will get this kind of lithium dendrites. You can see here that 2C, that means 30 minutes. If you change in 30 minutes, then you will get a lot of lithium dendrites. And we also compare the two protocol. This is constant charge, and this is overcharge. You can see that in the overcharged state, you will get a lot of lithium dendrites. And we also compare the signal of lithium dendrites. And if you use this kind of protocol, constant charge, and you can get a less, you will get a less dendrites. But if you charge it into overcharge to 4.6, you will get a lot of lithium dendrites here, and you will get a very, very strong here, light spots here. So we try to introduce some relaxation, because sometimes if you charge very fast, so you want to introduce some relaxation, and then the lithium ions will insert into the graphite. This is that's what we think about. So you can see here that there is some relaxation effect here up to 7.5 minutes, and then signal becomes stabilized. That means there's less dangerous here. But for the overcharge case, you have to wait another 15 minutes. So if you compare the two protocols without the relaxation, and then two protocols does not work very well, the capacity will decay very fast. But if you introduce maybe 12 to 16 minutes, and then for this protocol, constant charge CV is much more stable than the overcharge cases. And here, this is also compare the EPR images. Here, this is like constant charge, and this is overcharge. You can see that overcharge will still increase the signal of the lithium dangers. So that's why it's very important to stay 10 minutes after you fast charge your car. This is a mechanism you use. If you overcharge, you will get this kind of long dangers. In SEM, you will get this kind of signals here. But if you charge slowly or not overcharge, then this kind of loose dangers, this kind of loose dangers here. At last case, we'll talk about how to use for the auto-solid batteries. But for the auto-solid batteries, it's much more important to use the in situ EPR imaging, because for liquid state batteries, lithium metals and separators can be pure off because they are much more easy to pure off. But for solid state battery, it's not easy to pure off because they connect to each other very strongly. So we started a model system here that we used this as a castle and coated on the copper foil here. So this is a copper foil. This is the iron alloyed. And you can see that if we add a pressure, then it will work very well. If we don't add a pressure here, then this battery will short circuit very fast. So we introduce this kind of imaging, laser imaging here. This is laser imaging. So the A is the positive part, the B is the negative part. So this laser will indicate the size of lithium dangers here. So if we the laser is equal to 5, and the size of lithium danger is very large. But it depends on the field. You have to care about the field if you use L band. And so if we allow the pressure, and then the peaks will be very the area will be very much small, and the dangerous and will be very large, like 2.3. And but if you add the pressure into the solids, the batteries, you will get a large area, but you will get a small dangers. And also we have a patent here show you how to design and inside the instrument. And of course, we can do the several cycles, but I will not go to the details. And you can also use the NMR to detect lithium dangers here, such as this is the signal for lithium dangers on the solid electrolyte. So they are very strong. But if you add the pressure, and then the signal is very much more less. And this is the last case that we after the study of this kind of pressure, we want to study the effect of the size of this kind of lithium anode, because this is a real solid batteries, and the cathode and the electrolyte is roughly around with a diameter of 10 millimeters. But this kind of lithium metal is very small, and normally it's 5 millimeters, because we have to reduce the static reactions between these two lithium metals and solid state electrodes. But it's not easy to use expand, because normally the design is roughly around 3 to 5 millimeters. So we would try to use this kind of a large band with L band, but it's not very easy. But when we're going to do this experiment for several months, and we have reviewed a paper from Charles did one and then, and he also used the L-band imaging. It was published last November, maybe not published, but show up in next November. He used L-band to image this kind of solid state battery, and he get this kind of signals. And he shows that how to monitor the punch cells with aluminum plastic film. And when I review this file, I asked to compare the solid state battery without with the plastic film. That's it. And this paper was show up last November, and I really appreciate this work because I didn't think about the problem of this kind of aluminum plastic films. But we do it for different things. And we also use this pattern. We design this kind of L-band with large size, and the diameter is roughly around 8 to 10 in diameter. And for this kind of shape, if you have a small round shape, and if you measure the distribution of pressure, and you can get this roughly this one. But at the beginning, we are not going to get any signals if we do not charge it and discharge it. So normally we don't get any signal at the beginning. But if you charge it up, maybe after 1 cycle or 5 cycles, you will get the signals here. And it's obvious that the signal the lithium was placed roughly around this field in the middle of this kind of pressure center. And but in this node, it will does not work very well because there's a soft shortcut after maybe 1,000 cycles. So it's now very stable. So we designed another shape with a ring shape. We cut like this one, and we measured pressure distribution like this one. It's also like a ring, but it's not exactly. But the performance is much more better. You can roughly run to 300 cycles. And this is the imaging, and you can see the lights. Of course, the EPR, lithium plates on the plates will have a strong pressure. And this is the photos of the two lithium metals here. And of course, we also image the ring effect with one side. You can see here that you can strong stroke here. And we also compared with the many cycles, such as in 20 cycles and in 100 cycles. You can also see that in 100 cycles, the EPR image is in the center. For the ring shape is around a ring, so it's much more easy to observe that where is the pressure and where is the EPR lithium dangers. And we also compare the L-band and X-band because it's difficult to use the X-band for the 10 diameter with the 10 millimeters. So we cut the plate into half. So we also only observe the half the signal of this plate. You can see the signal is like this one in the L-band, and in the X-band you have a good light vision like this one. So we can still use this X-band if you don't want to do this kind of in situ experiments. And at last we mentioned that we also build this kind of a high pressure NMR probe for silicon anodes. And if we change the lithium anode to silicon anode, the main problem is that the silicon anode experience large expansion, so it needs a big pressure. For lithium anodes, it's roughly around 5 to 10 megaparts, but a silicon anode we need 30 to 100 megaparts. And this is the signal that what we get. You can see that charging the high voltage, you can get a signal of this kind of lithium silicon anode. And we are maybe within 3 months, we will publish the results. This is a signal of the lithium. At last, we are showing how to detect the metal cluster with going fast. This is to use EPR imaging to detect chromium. And for this kind of sodium batteries, if you increase the voltage, you will now work and becomes irreversible. So it's very interesting phenomenon. So at a low voltage, the in-situ imaging is totally reversible. But if you go to high voltage, such as 4 volts, you will get a new signal here. So we assign this signal to the chromium 5. And this is a comparison of two in situ experiments. Of course, we can do some EPR imaging to see where it is. It's located in the middle, so it's in a separator. And at last, we propose a new mechanism that's a double-layered mechanism, chromium 3 and plus chromium 4, and we will dispropionate to chromium 2 and chromium 5. It's a mechanism. At last, we talk about we also use NMR to list different kind of samples. And if you for this kind of sodium batteries, you have to use the PJ metapause acquired good signals, especially for the lithium ions. And PJ metapause was developed by the Zion Gan and Professor Gregory. And this is a example that for this kind of titanium doped samples, if you don't dope the samples, then the signals for layer of the TM layer will move to the sodium layer. But if you doped with this titanium, and then the lithium ions will go back to the magnesium layer. So it's very interesting phenomenon showing that if you dope some titaniums, and then this will make the much more reversible for the lithium ions. And we also use the EPR. You can see that for dope samples, it's much more reversible for the oxygen redox. And we've also used the AMR, oxygen AMR to detect this lithium coal bank. You can see if we label these samples, you can see the change of signal from O3 phase, O3 phase, O3M phase, and H1 phase. So it's much more, it's a little bit sensitive compared with XRD. And we can also use oxygen to solid state battery, such as for the liquid batteries. After 50 cycles, you will get signals here. This is a binary signal. But if you charge in a solid battery, you will get another signal here, O3M bases. So that means that you have to surprise this O3MS or bases. Then you will increase the reversibility of the phase transitions. And we think about the National Kid Research Development Program and Broker CHL action team. Thank you for your attention.
All right, thank you, Bingwen, for this extensive and very interesting seminar about NMR and EPR of batteries. So the floor is open for questions. So anyone who has a question is welcome to unmute themselves and just ask the question to our speaker. So I might start with one. It's mostly like a technical question. When you discussed the solid state batteries and you took the image taking a difference between a positive and a negative signal, or a ratio between an A and B signal.
Yes.
Yeah, I didn't quite get what kind of information this method give you. Yes, exactly, this one.
Yeah.
What are the two signals? If you can explain a little bit.
Normally, if you have different kinds of line shape with the different kinds of AB values, right? And if if ratio is equal to 1, that means this is a very, very small dendrites. So
I
it's
see.
like a Dyson line shape. Since it's very small line, small dendrite. But if this value becomes much more larger, that means the dendrite becomes much more larger, and like the crystalline. So you can use this technique to detect the size of lithium dendrites.
Okay, so the more away is so the more distorted is the line, the more dendrites there are. That's what you're saying. Yeah. Okay.
Yes.
And what's the reason that gives you this line shape when you have more dendrites?
It's not like more dangerous. It's like in small dendrites.
Oh, I see.
Then you will get a signal with this kind of dispersion line shape. But if you are large dendrites, then you will get this kind of absorption line shape. In fact, something like this one.
Okay. Thank you.
You're welcome.
Any other questions from the audience? If not, I have another one, just a curiosity. How long does it take to get an image of, for instance, this sample, which is 2 millimeter, 3 millimeter by 3 millimeter? How long does it take experimentally?
It depends on resolution. Normally, if we want to get a good resolution, normally around 1 hour to 2 hours.
Per image. Okay.
But if you don't want to get a very good resolution, and you just want to see what roughly around, and then you can use the 40 minutes to 30 minutes to get a rough image. Yeah.
And about sample sizes, you said that for S-band, of course, you have larger sample sizes, and X-band you are limited in that regard. So I suppose X-band is a few millimeters. S-band is what are the dimensions there?
Roughly, according to our design, it's like this one, and for X-band it's roughly around 3 to 5.
Oh, yeah.
And for L-band you have 8 to 10 in them because you have a lot of outside PVDF polymers outside to make it works from a solid state batteries. So the wall it's a much it's not a single one, it's a thick one.
It's a thick one, okay.
Yeah.
And the magnetic field homogeneity is enough to have to cover this large area.
Yes, because we tried in experimental that in this expand roughly 3 to 5. Oh, sorry, it's not. Sorry, it's a mistake. It's millimeter. It's not centimeter. Sorry.
Oh, I see. Okay. Okay.
I have changed the slide. Yeah, sorry.
Okay.
Yeah. Sorry, this is a mistake. Either you're right. We have tested experimental at roughly 3 to 5 millimeters in diameters. We will get a much more good homogeneity in this machine. If you become very large, it's not so inhomogeneous.
Okay.
Can I ask you one question?
Absolutely, go ahead.
Yeah. So how much in L-band, how much power did you use when you do the imaging?
I think roughly around 30 megawatts to 40 megawatts. It's because we have strong power, and because the signal in L-band is very, very weak. If you send a weak power, and then you will get a very, very weak signal, and it will take you a very, very long time to apply it.
So when you use that high power, whether that high power can distort the structure of the EPR centers?
Yes. So if you send a very weak power, because the solid electrolytes will absorb the power.
Yeah.
So if you send a very weak power, then you will not get a signal. So you have to send relative strong, maybe at least 20 to 25. You will get some signal. But if you increase to 30 to 35, it's much more tough if you want to decrease the experiment time.
So what is the gradient do you use?
In fact, we have two gradients. One is 2D gradients, maybe when it's roughly around 200 G per centimeter. We have another gradient, three-dimensional gradients, roughly around 50 G per centimeters. And in this case, we use I think we use the three-dimensional coils. And yeah.
Okay, thank you. Yeah.
You're welcome.
Questions from the audience? Doesn't look like. If there are no further questions, I would close the seminar here. So thank you again, Bingwen, for giving a seminar, and thank you to all the participants to join this session, and I'll welcome you to join the next one, which is in a couple of weeks, I suppose.
Okay, thank you for your invitation, and I hope next time I will join this Zoom much more easily.
Yeah,
See you
yeah.
next time.
Yeah, that's good that you pointed out these difficulties from joining from China. We will look into that, definitely. Yeah, we were not aware. All right, thank you very much.
Okay, you're welcome. See you.
Bye.
See you. Bye.